For number 3, we are looking for boiling point. We are given the mass of the solution, that is 0.300 grams. We have the molar mass, that is 60.10 grams per mole. The mass of the solvent is going to be 10.0 grams. And then finally, our Kb is given to be 0.512 degrees Celsius. This says inverse molality. So inverse molality, if molality is moles per kilogram, inverse would be kilograms per mole. So kg/mole for those units. We have our equation be delta T is equal to IKM. In this case, since we're looking for the boiling point, that's going to be the final temperature. So we can take this delta and make it final minus initial equals IKM. And at this point, we are just plugging and chugging. So TF is what we're looking for, minus TI. Well, this is a solution of water, so 100.0 degrees Celsius is the initial boiling point. If it doesn't say anything about what substance it is, I mean, it says it's urea, but we don't know the formula. We don't know if it's ionic. We haven't learned about that stuff yet. So we could just assume that I is 1. And then for K, it's 0.512 degrees Celsius kilogram per mole. And then finally the molality. So over here we have mass of solute divided by molar mass. That would give us moles. So 0.300 grams divided by the molar mass of 60.10 grams per mole will give us the moles, all divided by the kilograms of solvent. And so over here it's 0.010 because I moved the decimal 3 to the left, and then I need one more digit here, kilograms. And so 0.0100 kilograms, and we are just solving at this point. To solve this, I'm going to take, and I'm going to do the right side first. So 0.3 divided by 60.1 divided by 0.01 times 0.512. That's the right side, and then I'm adding the left side. And so right now, sig figs wise, I have 3 on the right side, so 0.255, but I'm adding the left side, which is only significant to the tenths. So since I'm adding, I have to abide by sig fig rules and round to the tenths. And so my answer is going to be this right side plus 100. So my final boiling point is going to be 100 point, and then rounding to the tenths, 3 degrees Celsius. So that is that first one. The next one is going to be a similar, well, I mean, they're all the same setup, but for this one it says, what is the molecular weight? So the molecular mass, we don't know. The mass of the solution or the solute is 7.39 grams. From those, we'll get the moles. The mass of the solvent is going to be 85.0 grams. I can convert that to kilograms right out the gate, 0.0850 kg. Delta T tells me that the final temperature is 82.6, the initial is 80.2, so 82.6 minus 80.2, and then Kb is given to be 2.52 degrees Celsius, inverse molality. So my equation is delta T is equal to IKM. My substance, it doesn't say, it's an unknown substance, so I is assumed to be 1 in this case. So delta T, plug it in, 82.6 minus 80.2 degrees Celsius. I, we're assuming to be 1. K is 2.52 degrees Celsius per molality. And then we need our molality. To determine the molality, it's going to be molality is equal to the moles of the solute divided by the kilograms of the solvent. We can get the moles of the solute by taking the mass divided by the molar mass. So I'm just going to plug in that quantity in the numerator. So mass divided by molar mass. Well, actually, I know the mass, so I could put that. So this is going to be 7.39 grams divided by the molar mass, all divided by the kilograms of solvent. And so that's going to be 0.0850 kilograms. And so now I'm just ready to solve for my molar mass down here, and then I will be all set for this problem. To do this, I'm going to first solve on the left side. So 82.6 minus 80.2, and so that is 2.4 degrees Celsius is equal to, and I'm just gonna go ahead and say 2.4. I'm gonna move the mass over, so times 0.085. And now I'm going to, let's see, I'm going to divide 2.52 on both sides. So I already moved my mass over here with the temperature, so I'm going to divide by 2.52. And now I have 7.39 is equal to this, or 7.39 divided by molar mass is equal to this. And so to solve that, I'm going to say, okay, 7.39 divided by that mess, and that allows me to solve for my molar mass, and my molar mass is 91.28. And for sig fig purposes, I have 3 all through here on this side, and then I have the difference is just to the tenths, so I'm precise to the tenths. So if I'm adding, if we subtract this and we get 2 sig figs, and then we have 3 sig figs over here and we multiply, we're going to end up with 2 sig figs. And so my answer here is just going to be 91 grams per mole for the molar mass of this substance. The next one, it says calculate the boiling point. Okay, so T sub B is unknown. Molality is 0.250, and the pressure, we don't need it. Colligative properties aren't going to have to do with that because we're not dealing with pressure, we're dealing with boiling points. KB is 0.512 degrees Celsius per molal. It tells me that my substance is FeCl3, so FeCl3, I could see that if I were to break this into components, I would have iron, I would have chlorine plus chlorine plus chlorine. So these are the charges on these. Actually, that's a 3. You don't need to know these at this point in the course, but we do know that we have 4 particles, so the Van 't Hoff factor in this case is going to be I equals 4. So my equation is delta T is equal to IKM. Delta T, I'm looking for my final. The initial is going to be 100.0 degrees Celsius because it's pure water. I has already been established before. KB is 0.512 degrees Celsius per molal. And then the molality is given to be 0.250 molal. This one is easier than the previous ones. So we have 4. Let me make sure my calculator screen's on the paper. So I have 4 times 0.512 times 0.25. And then I'm going to add 100 to both sides. And so the 100 is only precise to the tenths. And so my calculator is will only be precise to the tenths as well. So 100 plus my answer, it's 100.5 is my answer. So TF, the final temperature after I've added that salt, is 100.5 degrees Celsius. Number 6. 6 It's asking for the molar mass. It gives me the mass of the solute to be 1.42 grams. The mass of the solvent is going to be 25.0 grams. I'm going to need kilograms, so I can convert that immediately, 0.0250 kg. My delta T for my freezing point is 1.96 degrees Celsius. It's depressed that much. And then my KF, running out of space, is 5.12 degrees Celsius per mol. It doesn't say what the substance is, so we're assuming I is 1. So I have delta T is equal to IKM. Delta T is given to be 1.96 degrees Celsius. I is 1, K is 5.12 degrees Celsius per mol. Molality is going to be the moles. I can get the moles from the top two there. And so that's going to be 1.42 grams divided by my unknown molar mass. That's the moles divided by the kilograms of the solvent, 0.0250 kilograms. And I'm solving for my molar mass, very similar to problem number 4. So let's do this. So I'm just going to start with 1.96, and I'm going to move this piece over. So times 0.0250, and then I'm going to move this piece over by dividing on both sides. So divided by 5.12. Now I have 1.42 over molar mass is equal to this. So to solve that, it's just going to be 1.42 divided by my answer. So I get an answer of 148.37. In terms of sig figs, I have 3, 3, 3, and 3. So my answer is going to have 3. 148, and then grams per mole. The last one. It says, what is the freezing point? So T sub F is unknown. The molality is given to be 0.100 mol. I have aluminum chloride, so that suggests that I have an I of 4. The KF is given to be 1.855 degrees Celsius per mol, and then I is 4. I already got that. Okay, so delta T is equal to IKM. I'm looking for my final. This is a solution of water, so it's going to be the final minus the initial is equal to IKM. The final is unknown. The initial is 100.0 degrees Celsius. I is 4. K is 1.855. That's an 8. 1.8. I'm just going to rewrite it. 1.855 degrees Celsius per mol. And then my molality is given to be 0.100 mol. So I'm just solving for TF. To do that, it's just going to be the right side, so 4 times 1.855 times 0.1, and then I'm adding 100.0, so I'm going to be rounding to my tenths. So 100 plus my answer, I have a final temperature of 100.7 degrees Celsius.